Testing. 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 All right, I think we're good. All right, welcome to another Hoopo stream. Hope everybody had a good weekend. We are starting off strong today. We're starting off with a paper here called Consistency Models. This is a paper coming out of OpenAI, which is a bit unusual, right? They decided to be super secretive, and then here they are releasing a paper. This is Ilya, who is, of course, the famous co-founder, kind of the more technical one. And this probably, if I had to guess, he probably has some people under him that are a little bit more technical, almost trying to recreate a more academic kind of feel. This feels very, very academic. It's very math heavy. You guys better be ready because the math here is intense. So it's not a very long paper, but it's an extremely dense paper because of this math. So we're going to do our best, and we're going to see if we can discover any new interesting things. Quality. So okay. This was released 2nd March. A little bit old now, but there it goes. Given a probability flow ODE, so ODE means ordinary differential equation. So basically, differential equation is usually it's sets of equations. It's like basically these sets of equations that describe system and its derivatives. So like they're very common in, for example, physics, where you might have a system that describes something. My ODE knowledge is dated at this point, so we're going to have to probably end up using GPT. So probably end up using good old GPT here to explain to us some of this stuff. But a probability flow ODE that smoothly converts data to noise. Okay, so this is the kind of diffusion model paradigm here, right? Diffusion models start with noise, and then over time they iteratively kind of refine it into the actual image. It's a form of image generation. And they're doing this over a variety of steps, right here indicated by 0, t, t prime, and then capital T. We learn to map any point, xt, xt prime, and xt capital, any point here, on the ODE trajectory to its origin, x naught. Okay, so you see they have some function here, f theta, which is going to be their neural net, and the neural net takes in some point xt, as well as the time, and then produces the final image. So models of these mappings are called consistency models, as their outputs are trained to be consistent for points on the same trajectory. Okay, so I think I understand this concept. Whereas diffusion models, there's some fixed amount of steps, right? Whenever you train a diffusion model and whenever you're performing inference on that diffusion model, there's some fixed amount of steps that were used, and each step removes some amount of noise. And so you're going to have to do a bunch of these inference steps, and it might take very long. And we've seen some papers where people try to do it in one step, people try to do it in less steps, and they have their tricks for doing so. And this seems to fall into the category of papers where they have a trick for trying to do it in less steps. So the whole point here is to not have to do these 10 steps, these 10 different time steps, and instead do it in one step. So they're learning this ordinary differential equation parameterized here. It's f theta. And this f theta is going to be able to basically go from any point along this continuum of image to noise and map it into the original image. Not the original image, but the image that you want to generate. So it's all about basically making these diffusion models faster. All right. Go to it. Abstract. Diffusion models have made significant breakthroughs in image, audio, and video generation, but they depend on an iterative generation process that causes slow sampling speed. Yeah, this is slow. Right? You have to perform these steps, and these very nice diffusion models can take like 10 steps, right? And each step is inference on a model, so you get very slow, very quick. So obviously people want real-time image generation that's based on diffusion models, so this is a trick to do. Propose consistency models, a new family of generative models that achieve high sample quality without adversarial training. They support fast one-step generation by design. Okay, that's the key. While still allowing for few step sampling to trade compute for quality. Oh, okay, this is more interesting. So this is actually super powerful, right? We've seen other papers where people come up with a trick to basically reduce the amount of steps required to generate, but I don't know if I've seen a trick that also allows you to kind of trade it off, right? So in diffusion models, one thing that's popular is this kind of like classifier-free guidance, right? Where you have this like guidance vector that conditions your denoising, and then you can change that the strength of that kind of like guidance weight to have something that's either very closely related to the specific prompt or something that's not closely related to that prompt. So this idea of kind of being able to trade off the relatedness of your image to your prompt is kind of parallel here to the ability to trade off quality and speed, right, in a more continuous way. So that's a very nice little feature here. They also support zero-shot data editing like image inpainting, colorization, and super. I mean, these are kind of the standard things that come with these image generation models. Without requiring explicit training on these tasks, I would say pretty much all the other papers don't require explicit training on that task, so that's not complex. Consistency models can be trained either as a way to distill pre-diffusion models, as a way to distill pre-trained diffusion models, or as a standalone generative model. Distilling pre-trained diffusion models, that to me means they're going to probably use stable diffusion and then or DALL-E and then distill, which basically means not quite fine-tune, but in fine-tuning you're changing the model itself. You have some pre-trained model, and then you're changing the weights of that model itself. In distilling, you're taking a pre-trained model and you're training a new, usually smaller model based on the inputs and outputs of the original pre-trained. Through extensive experiments, we demonstrate that they outperform existing distillation techniques for diffusion models in a 1 and we achieve a new state-of-the-art FID on CFAR 10. State-of-the-art FID on CFAR 10 literally means nothing, IMO. Because CFAR 10 and ImageNet 64x64, these are very, very grainy, small little thumbnails. So combination of a very tiny, very grainy image with a somewhat bogus quantitative metric like the Frechet inception distance, I think makes this doubly bogus. So when trained as standalone generative models, consistency models also outperform single-step, non-adversarial generative models on standard benchmarks like CFAR, image, or other benchmarks here. LSUN is like the inside of rooms. LSUN data. Yeah, this LSUN is. It kind of looks like the pictures of hotel rooms, a hotel website, but it's also 256 by 256, so it's actually quite great. Okay, introduction. Fusion models, references. Also known as score-based generative models. I have not used that term. Achieve unprecedented success across multiple fields, including image generation, which I think is what they're mostly known for. Audio synthesis, I feel like this is more kind of a novelty use case, and video generation. Unlike generative adversarial networks, which are also quite popular, and they've been making a comeback, and there's been papers, I forget exactly which one, but there was one that we reviewed earlier on the channel that was a GAN that was somewhat competitive with diffusion models. So GANs aren't dead yet. They've kind of come back from the dead, but who knows? Maybe these ODE models beat both traditional diffusion models and GANs. These models do not rely on adversarial training and are thus less prone to issues such as unstable training and collapse. Yeah, so GANs are very difficult to train because you kind of fundamentally have this generator and discriminator, and if those ever get out of balance, basically end up not learning anything. If the discriminator gets too strong compared to the generator, then end up with this mode collapse, right? Mode collapse kind of means that the distribution over the kind of embedding space collapses into like a very simple distribution. It's like all of it always ends up being 0. Additionally, diffusion models do not impose the same strict constraints on model architectures as in autoregressive models. Okay, variational autoencoders or normal flows. Okay, so diffusion is a more general technique, and you can use it with a variety of architectures. Key to the success of diffusion models is their iterative sampling process. It's key, but it's also the Achilles heel of them, right? It's because you have to iteratively remove this noise. They kind of take forever, right? If you guys use Midjourney, you type something and then it shows you that image, and first it's a blurry version of your image and then it kind of progressively gets less blurry. What's happening there is that it's running the same network again and again and again in order to like slowly move the image away from being noise and into whatever you actually want. This iterative refinement repetitively evaluates the diffusion model, allowing for trade-off of sample quality. So this is now the second time they've mentioned this, and I'm curious to see how this actually works with their model, but it seems like they've figured out a way for some kind of weight, right? Probably going to be some number between 0 and 1 where you can choose how many steps you want to run the kind of denoiser for, and then that'll result in basically this trade-off that where you can say, okay, I want to run it for many steps because I want the highest quality possible image, or I want an image in 1 step because I just want it to be fast, and thus the trade-off for compute versus sample quality. By using extra compute, a small size model can unroll it into a larger computational graph and generate higher quality samples. Iterative generation is also crucial for the zero-shot data editing capabilities, enabling them to solve challenging inverse problems ranging from image inpainting, colorization, stroke-guided image editing, or computer tomography and magnetic resonance imaging. What? MRIs? CT scans? What is going on here? Are they actually going to generate MRIs and CT scans? I don't know if I've seen that before. I've definitely seen diffusion models generate like standard RGB 3-color images, but I've never seen them generate more complicated modalities. Compared to single-step generative models like GANs, VAEs, and normalizing flows, the iterative generation procedure diffusion model typically requires 10 to 2,000 times more compute. Yeah, which is why GANs have kind of been making a comeback, is because they only need 1 step to perform inference. Our objective is to create generative models that facilitate efficient single-step generation without sacrificing advantages of refinement. Built on top of the probability flow ordinary differential equations. Kind of key math concept here. Whose trajectories smoothly transition the data distribution to traceable noise distribution. So here, right, you have the diffusion model, and it's going from noise into the image, right? And it basically, the way normal diffusion models work is they do this kind of step by step, but the way that this probability flow ODE consistency model works is it goes straight from any step along this continuum into the original first step here. And math, largely what you're doing is you're starting from noise here, which is represented by a normal or a Gaussian, right? And you're going backwards into the actual data distribution. Here is represented by kind of two Gaussians together. So this is just an approximation, right? But like at the end of the day, an image is basically just a probability distribution in pixel space, right? Different color pixels have different probabilities, and thus what you're really doing is mapping one probability to a different probability. I don't know exactly what they mean by trajectory here. I guess each pixel takes a trajectory over the time, right? So in this image, right, you can say that the pixel here that represents the eye, right, like it starts off and it's, I don't know, like some weird combination of red, green, and blue pixels, and then it kind of moves and then becomes this kind of darker pixel, and then black, and then black, and then black. So like maybe that's what they mean by trajectory. It's kind of that each pixel has some kind of trajectory. We propose to learn a model that maps any point at any time step to the trajectory starting point. Notable property of our model is self-consistent. How did we learn what specific noise function is best for this process? Would other things like Perlin noise versus Gaussian make a difference in metrics? So there is different noise distributions. There was a paper that we read a while ago at this point, but basically there's a bunch of different noise distributions you can use, and they have different trade-offs. I don't think this is like telling us that it is a Gaussian. I think they're just showing you a Gaussian here because that's kind of the easiest thing to visualize, and it just represents a distribution, but I don't think the noise distribution itself is necessarily a Gaussian. It might be more complicated than that. Transformation of Gaussian. Yeah, I think this is like not literal. It's figurative. I don't know if figurative is the right word. It's symbolic, I guess. Analogy. A notable property is self-consistent. Points on the same trajectory map to the same initial point. Points, I suppose, are pixels. We therefore refer to such models as consistency models. Consistency models allow us to generate data samples by converting random noise vectors and points of ODE trajectories with only one network evaluation. By chaining the outputs of consistency models at multiple time steps, we can improve sample quality and perform zero-shot data at the cost of more. So, probability flow, ordinary differential. They introduced this here, but I don't know if this is actually a existing concept. So let's ask good old probability flow ODEs. Can you explain probability flow ODEs? All that generates, let's create a consistency model. We offer two methods based by enforcing the self-consistent property. Can it be some kind of regularization or loss term that reinforces this consistency. First method relies on using numerical ODE solvers. So there's a lot of different ways to solve these ordinary differential equations. Like in your differential equations in college class, you're probably learned like 20 different ways to do it. And numerical here means basically approximations, right? Where you're like trying A and then A is too small, and then trying B and then moving in between those and so on. So like you're not solving it kind of symbolically, like with the symbols and math and canceling things out on both sides and then getting an answer that's perfect. You're basically plugging numbers in and then over time iterating on the numbers. So that's what a numerical solver is for ODEs. And a pre-trained diffusion model to generate pairs of adjacent points on a PF-ODE trajectory. So probability function, ordinary differential equation. Generate pairs of adjacent points. So I guess within this trajectory, here's the pairs of adjacent points. You maybe have a point here and then a point here. It doesn't seem like the points ever kind of start and end in between. It seems like they always maybe start somewhere on the trajectory and then always end at the very beginning. Minimizing the difference between model outputs for these pairs. Okay, so minimizing the difference. So, right, you see here how they hinted at some kind of regularization. Generally okay with people asking AI, ML guidance or advice as beginners? Yeah, sure, man. Feel free to ask any questions. You know? I might not be able to answer them, you know, like I'm confident in my math, but this paper is very intense, so we're definitely gonna have to look up some stuff. Like, for example, what a probability flow ODE is. So let's see. Probability flow ODE is a concept that combines probability theory and ordinary differential equations to model the dynamics of probability distributions over time. Okay. It's a framework to understand how a given probability distribution evolves or changes over time. Okay, that makes sense. So the same way that you might have a differential equation that represents the mass of some like vat of liquid, and then like there's holes and the liquid leaves, and then you have basically mass flow. Like that's the types of differential equations that I'm used to, right? Coming from my background in physics. But it seems like you could just basically take that concept and apply it to probability distributions, right? You have some probability distribution and then like a Gaussian, and that's changing over time. And then that's basically what it seems like these are, is basically differential equations that describe the change of a probability distribution over time. Particularly useful in areas such as machine learning, physics, and finance, where the behavior of systems often involves stochastic processes or random variables. A random variable in this case might be the prompt, right? The prompt gets encoded into a vector, and then you want to condition the diffusion process on that vector. Break down two main concepts: probability and ordinary differential equations. Describe the relationship between a function and its derivative. Right? They express how the rate of change of a quantity is related to the quantity itself. Time evolution of the probability distribution given by an ODE that involves the probability distribution time derivative. What is the time derivative of a Gaussian distribution? Does that even make sense? Goal is often to find the probability that satisfies the ODE given some initial conditions and boundary conditions. This can be done using various numerical or analytical techniques. Developing machine learning algorithms that can learn the dynamics of complex systems by observing their behavior, which is exactly what kind of we're doing, right? We're basically, we have some probability distribution and it has some trajectory over time, right? And it starts off as just a pure noise distribution, and then the distribution that it gets to at the end of its quote-unquote trajectory is going to be the image, right? The image itself, you could also think of it as some kind of probability distribution. So we're moving from how do you go from noise to image into how do you go from noise distribution into image distribution. So basically they're just adding the word distribution there to kind of make it sound fancy, but that's really... Yeah, it seems like they're learning the trajectories, which allows them to skip the iterative steps. I agree. I think that's a good summary, Jake. This approach situates consistency models as an independent family of generative models. Yeah, different from diffusion models. Just the idea of the diffusion model is there for sure. Either approach requires adversarial training, and both training methods permit flexible neural network architecture. Challenging. I don't know if CFAR 10 is a challenging image benchmark. I feel like CFAR 10 is like the easiest possible thing to do. Maybe not a little bit harder than MNIST, but it's still going to be very easy. Empirically, we observe that as a distillation approach, consistency models outperform progressive distillation. I guess this is another kind of secret technique that people came up with. You might have even read this paper, but I'm too slow to remember. Across a variety of data sets, consistency models reach new state-of-the-art FIDs for one step. I've ranted on FID before. I just don't think it's like a very good metric, so state-of-the-art FID is kind of meaningless to me. We then trained as standalone consistency models achieve comparable performance despite having no access to pre-trained diffusion models. They are able to outperform many GANs and all other non-adversarial single-step generative models across multiple data sets. So GANs are single-step generative models, but they're also adversarial whenever you train them, so it makes them more annoying to train. So they're saying it outperforms any of the other things that aren't single-step. There was a diffusion model. Is this the paper that we read? In this paper, we introduced PyA requiring less than 10 steps. So yeah, so this paper, the cool thing is they were like, wow, look at that. You only need less than 10 steps, right? But like here now you have consistency models, you only need one step, right? Perform zero-shot data editing tasks. Okay. Diffusion models. All right, let's see how they describe diffusion models. This is where we're going to start hitting the math quagmire here. So it's going to be slow progress for sure. Continue time diffusion models inspire the consistency model. Diffusion models generate data by progressively perturbing data to noise via Gaussian perturbations. So was it that was asking what the noise distribution is? It's Gaussian. So when you're training a diffusion model, you're adding noise, right? And when you're performing inference with a diffusion model, you're removing noise. So it's a little bit confusing, but when you perform inference, you're actually going from capital T time step, all the way to time step 0, right? So you're actually going backwards in time when you're performing inference. But when you're training a diffusion model, you're starting from the actual image and then you're adding the noise. So you're actually going from 0 to capital T. So the kind of like the direction of time flips whether you're in training mode or you're in inference mode, like eval. Just another way to say eval. Let P data X denote the data distribution. So this is the data distribution of the actual image itself. Diffusion models start by diffusing P data with a stochastic differential equation. Stochastic here, just random. dxt, so derivative of xt, which is the image at time t, equals mu xt t. So this is like some distribution or some function, right? So mu and sigma here are usually representing the mean and the variance, right, of a distribution, like a Gaussian, right? The mean is just like kind of how centered it is, and then the variance is kind of how wide it is. So this is some kind of the derivative of x, the image, is some function that describes the mean, which is a function of the image itself, and then also some time t, dt, and then here the variance dwt. T is the time that we're describing, right? So O is greater than 0, generally maybe 10 different time steps, right? If we look at the pi example, but there's diffusion models that have many more time steps. Mu and g are the drift and diffusion coefficients respectively. What is the drift? I've heard that. I guess maybe the center of the Gaussian, like if it moves, it becomes, you call it a drift, like it drifts. Weird. WT denotes the standard Brownian motion. Okay, that's kind of interesting. So Brownian motion is basically kind of like just random motion, like you've probably seen GIFs about this. A Brownian motion GIF, right? This is what it looks like. It's just, this is the position of a point in space that's executing Brownian motion. Is just basically randomness. So, right, because we're talking about trajectories over time here, right? What is the trajectory over time of noise, right? Well, I feel like Brownian motion is a pretty good way to describe noise in the sense of like trajectory. That kind of makes sense. We denote the distribution of xt as ptx, and this result as p0x equals data x. Okay, so basically what they're trying to say here is that when we're at time step 0, right, so you have a probability distribution of the image over, and it's going to change at each time step, right? So pt here is just the probability distribution at time step t. And P0 here means the probability distribution at time step 0, which is when you should have the full image without any noise in it. And the full, at time step 0, the full image without any noise in it should be equivalent to the data distribution of the image, right? Remarkable property is the existence of an ordinary differential equation dubbed the probability flow ODE, whose solution trajectories sampled at t are distributed according to solution trajectories. Right, so we learned that a probability flow ODE describes the change of a probability distribution over time. Right, so as the probability distribution moves from the noise to this p data x, right, which is the distribution of the actual image, and those trajectories are distributed according to this. Okay, so you have, this is basically the same equation up here, except now the dt is pulled out here, right? So you have dxt, you have this mu xtt here, but you see how they pulled out the dt here. And by pulling out the dt, they changed this sigma t and dwt into this term here. This grad or curl, whatever it's called. The curl math symbol. Yeah. It's upside down triangle. Upside down triangle math symbol. It's just basically, but upside. Divergence. No, this is not what I want. Yeah. Just basically means. Okay. So the log of pt, so the log of the probability distribution at time step t, and they're calling this the score function. Right? We don't really know exactly what the score here means, but here they're drawing an analogy to the score-based generative models. Yeah, if you look at all these papers too, so notice how like Song et al. 2021, Song and Ehrman 2019, 2020, Song et al. 20. So like this Song dude here, he's probably the origin, or she is, or they is, they are the origin of all this kind of like hardcore math-based generative models, it seems. Typically, the SDE in equation 1 is designed such that P of Tx, right? So this is the probability distribution at time step capital T, which is basically supposed to be pure noise, is close to a tractable Gaussian distribution, pi of x. So they're basically saying at the time step capital T, which is the end of training or the beginning of inference, you're starting with a pure Gaussian noise distribution. We here, after adopted configurations who set mu xt equals 0 and sigma t equals 2t. So this is centered on 0. It's a Gaussian centered at 0, and then the variance, standard deviation, all words for the same thing, just basically how wide it is square root of 2t. So what does it mean to have the variance kind of be a function of t? Is that if t is very big, the variance is very big. A lot of potential values that distribution can represent. But as the time step t goes all the way down to 0, the variance should ideally flatten, and it should become very, very narrow, right? Very precise, just on a specific point. In this case, we have ptx equals p data x. This little symbol, I guess, here denotes the convolution operation, right? And here is a normal distribution centered around 0 with t squared as the variance, and then I guess sigma is the standard deviation, which is the square root of that, where you get the square root of 2t here. Oh, fuck. For sampling, so here you go. They said tractable Gaussian distribution, which represents the pure noise distribution. Then this is the actual what it is here, right? So the pure noise distribution at time step t, capital T, is centered on 0 and has t squared as kind of the variance. Make sure it's green. Green is the color I use for equations. Yellow is the color I use for general notes. And then red is the color I use for data sets, models. For sampling, we first train a score model. Okay, so they have a separate model here. You see how at the top of the paper here, they have this f of theta. So this is a function parameterized by theta. So this is going to be one neural network. And here you have the score model, S of phi. This is parameterized by phi. So this is going to be a separate neural network, right? They're calling it the score model. And the score model is a function that takes in x, the image, right, and the time step t, and then gives you, right, this little approximates this term here, right, this log pt, which they said is the score function. So the score model is just a neural net that tries to approximate the score function, right? At the end of the day, neural networks are just function approximators. They're trying to approximate some function. Okay, so score matching. I assume this is some kind of specialty loss that you can use to train score models. Then plug it into equation 2 to obtain an empirical estimate of the probability function ODE, which takes the form dx dt equals negative t s phi xtt. Okay. So equations 1, 2, and 3 here basically are telling a story, right? You're starting from this equation here. You're merely saying that the change of the image over time is the kind of this Gaussian here, and then you have Brownian motion. And then they pull out the dt, so they pull out the dt from both these terms, and they turn this kind of like Brownian motion term here into this more complicated log term which they're calling the score function. And then they say, okay, well, if we pull out this more once we have this kind of more complicated term here, which represents the score function, let's introduce a model called the score model. And we're just going to say that this score model is going to approximate this score function here. So we're basically going to replace this part here with this score model. And whenever you do that, you can basically, they're bringing the dt over to this side over here. So you see how dx dt, all they did was they took the dx and then they brought the dt over. So you have dx dt is now equal to negative, and then they replace all of this crap here with the score model. So that's the rough story of how you get from 1 to 2 to 3. And now that they finally have this equation 3, they're calling it the empirical PF-ODE. Okay, and that's the end of that story. So the next step, we sample x hat of t. I don't know what the hat here means, but x, capital T means at the very end, so it's basically the noise distribution, which is basically the noise is what they're saying here. Initialize the empirical PDF ODE and solve it backwards in time with any numerical ODE solver. Solve it backwards in time with any numerical ODE solver. So during training, you're adding noise. During inference, you're removing noise. If going forward in time is adding noise, going backward in time is removing noise. So the trajectory goes from the image distribution, right, this data over here, and it moves forward in time into the noise distribution. So you want to do actually backwards in time, right? You want to go from a point in the trajectory that is further ahead in time and then go back to a point in the trajectory that is more back in time. Okay, so they're using a Euler numerical solver and a Hune solver. I think this is the one that's more popular. I'm not exactly sure. There's a bunch of different ways to solve these, and that can get pretty hairy pretty quick. Let's actually... What are some differences and or advantages and disadvantages of using a Euler numerical solver versus a Hune solver for an ODE? Euler and Hune solver are both numerical methods for solving ordinary differential equations. It has its own advantages and disadvantages depending on the specific problem being solved and the desired level of accuracy. Okay, advantages. Euler is going to be easy, straightforward to implement, and easy to understand. Who cares about that? Speed, because it requires fewer calculations. But where does Euler solver go wrong? Accuracy, right? It's a lower order of accuracy. It's a first order solver, right? Whereas the Hune solver is a second order solver, which means it's going to be better. Euler method, I guess, is less stable. So Euler method is simpler, faster, but not as good. And then the Hune solver is going to be slower, more complicated, but better. So pretty standard kind of stuff there, right? You're generally trading off between an algorithm that's faster and not as good, and an algorithm that is slower but good. Avoid numerical instability. One typically stops the solver at time step sigma, epsilon. All fixed positive number. I don't know. I guess what they're saying here is that instead of using like pure time steps here, you're basically using very small, like kind of pseudo time steps. So E is probably 0.0 here. E is 0.002. right? If you think of t going from 0 to, actually here they go, it's 80. So normally you would have 80 steps of diffusion to get to the answer, but here they're going to do it in one. We rescale pixel values in image -1 to 1, so this is kind of standard normalization, right? When you're doing computer vision, you don't want to just operate on pure pixel values, right? The way that images are stored, generally the red, green, and blue pixels, they're kind of stored as uint8s, right? And they're stored as a number between 0 and 255. But if you just feed numbers between 0 and 255 into your model, it's going to take longer to learn anything, and it's just not going to be as good. So when you're using images in machine learning, you will rescale the values of those pixels from 0 to 255 uint8s into float 32s that go from negative. So this is just kind of standard image normalization. Fusion models are bottlenecked by their slow sampling speed. Clearly, using ODE solvers for sampling requires many evaluations of the score model. ODE solver and the existing methods for fast sampling include faster numerical ODE solver. So I think this is maybe the other papers that we read are basically, they're not necessarily innovating on the technique. They're just saying, hey, by the way, I work in math and you guys are using the Euler solver. You guys are scrubs. There's actually this little known cool kid solver that is much faster. So it seems like that's what previous techniques have done. However, ODE solvers still need more than 10 evaluation steps to generate competitive samples. Competitive samples. I mean, it's competitive race. Rely on collecting. While that using TF ODE, they are able to go from the static Gaussian outcome times. Yeah. I think basically the reason, so like I'm kind of speculating here, but I think the reason all of this works is because the trajectories are actually like smoother and simpler than we think, right? So in a diffusion model, right, like there's some, go back to this image, right? You're going from this noise and each individual point kind of has some trajectory over the space, right? And in our head, we might think that the trajectory is quite complicated, right? Where it's like, starts off as this kind of look, and then it goes here, then it goes back here, then it goes back here, then it goes back here, and then finally ends up in the right place. But it seems like the secret hidden truth of the universe that this paper is taking advantage of is that the trajectories are actually very smooth, and it actually goes, see, I think there's a reason that the lines here in this little graphic are very smooth, simple lines, and not just like some kind of like weird like noise, right? Maybe that's it. I'm just kind of speculating there. I don't really know what I'm talking about, right? But yes. Most distillation methods rely on collecting large data sets of samples, which itself is computational. A distillation approach that does not suffer from this drawback is progressive distillation, with which we compare our consistency. Propose models and type of generative models that support single step. Math is cool, man. I also think that, not to kind of distract from this paper, but I feel like math is also coming to its end. Right? Like, much like once we had externalized memories, like a cell phone, right? Humans lost their memory a little bit, right? We kind of lost some of our ability to do math once you had calculators, or at least arithmetic, right? There used to be people that were very good at that, very good at multiplying numbers, and they could multiply very big numbers very easily, but over time, because of calculators, less and less people learn that skill, and now it's actually a very rare skill, right? And I feel like in our new age of AGI, right, with these big LLMs that can basically, they can code, they can do math, they understand things, I think people are going to actually become stupider. And it's going to actually be incredibly rare to have a human being that still has math knowledge and still knows how to do math things. So we might be the last generation of people that actually give a shit about math. And, maybe it doesn't matter, because, like, the mathematicians of the futures will be LLMs, and no human will be able to understand what the hell they're even talking about. But it doesn't matter if we're just all in VR playing video games all day. We propose consistency models. All right, finally we got to the actual meat of this paper. Support single-step generation at the core of its design while still allowing iterative generation for zero-shot editing. Models can be trained in either the distillation mode or the isolation mode. Kind of two different ways that you can train these. In the former case, consistency models distill the knowledge of pre-trained diffusion models into a single-step sampler. Okay. Okay, so the distillation here, right, distillation is when you're basically training a new model by having it kind of copy the original model. So what does distillation mean in this context? In this context, it basically seems like what they're saying is that they take, let me just, rather than scrolling up diffusion models, have a picture. Yeah. So it's also of a cat, which is very fitting. So what they're going to do, the way that they're going to do this distillation is that basically they're going to say, I have a pre-trained diffusion model, such as Stable Diffusion, and I can actually ask Stable Diffusion, what does the image look like at every single intermediate step? So I have basically this Oracle model that's going to tell me, here's how you diffuse from Gaussian noise to a cat. And then all we're doing here is we're saying, okay, well, if you have this trajectory that goes from Gaussian noise into a cat, I'm basically going to train my consistency model to say, okay, can you go from this image to a cat? Can you go from this image to a cat? Can you go from this image to a cat? Right? So it's like you're going to sample random pairs of points where one of them is like closer here to the noise and then one of them is closer here to the actual image. And then you're basically just going to train the consistency model with those pairs, right? Those input-output pairs. Stuff going on here. They're going in the opposite direction. It's not the static Gaussian, but the image, they go from the 80th time step to 0. Yes, when Aradhya, hope I said that right, but yeah, they are training. When you're training, you're kind of going, you're adding noise, and then when you're inference, you go backwards. So 0 to 80 or 80 to 0, depending on whether you're adding noise or removing. Euler discrete and more complex solver is not that significant qualitatively for good approximation. Okay, so Popo, you're saying that Euler versus these Kuhn methods are basically about the same, and maybe we should just use Euler because it's faster? Good to know. Okay, in the later case, consistency models are trained in isolation with no dependence to pre-trained diffusion models. Okay, so in one way, they're going to be basically using a pre-trained diffusion model, which I almost bet you is going to be Stable Diffusion, or maybe not, maybe it's DALL-E, but they're going to basically use it to get pairs of trajectories or images and their noise. And then they're also going to be training this from scratch, probably just as kind of a sanity check to make sure that you could train these from scratch. Below, we introduce the definition parameterization. Parameterization? Is it parametrization or parameterization? I don't know. And sampling of consistency models plus a brief discussion on their applications. Okay. Right. It's going to start getting hairy here. Like, kind of a personal pet peeve of mine is this kind of stuff here, right? Like, when you put math inside the paragraph, it just makes it so much denser for no reason. Okay, so you have a solution trajectory. So xt with t going from sigma to t. So if you noticed, if you remember here, they said that they don't want to go all the way to t equals 0, right? So they're going to go to t equals this 0.0002, right? So this small number here. So instead of the trajectory going from 0 to capital T, they're going to now go from this little sigma to t, probably because of just numerical stability issues. So you have some solution trajectory which has these steps, right? And you can think of this as a trajectory, right? You have time step capital T, time step capital T minus 1, T minus 2, T minus 3, and so on. And actually, I understand now why they're doing this. So one way to interpret this little small fixed positive number is that the image never really has all the noise removed, right? Like, if you went to t equals 0, what you're basically telling the model is that at t equals 0, there should be no noise whatsoever. But if you only go to t equals 0.002, you're telling the model there's still some tiny amount of noise here, right? We define the consistency function as f. So you're going to have a function, and then you're probably going to have a function approximation for it. So yeah, here you go. We're kind of cutting to the chase here, but they're going to say here's a function which maps from xt and t to x 0 or x sigma, right? The like very first image. A consistency function has the property of self-consistency. Its outputs are consistent for arbitrary pairs that belong to the same trajectory. So regardless of whether you give it an x of t that's very close to the capital T time step here, or whether you give it an x sub t that's very close to the time 0, it should be consistent. It should give you the same image regardless of what this pair is, right? So how are they going to train this? In the distillation kind of method, they're going to say, okay, the trajectory from here to here, right, should be the same as the trajectory from here, right? And that's that kind of self-consistency that they're talking about here. fxt equals fx t prime for all t and t prime. Okay, so basically t and then t prime here is basically the two steps, right? So interestingly, they don't have an additional condition here. I would have assumed they said, okay, t and t prime are sampled from sigma to capital T, and then t is always less than t prime, right? Like I would assume some kind of thing like that, but they don't have that in there, which means that maybe flip them. I don't know, that doesn't seem like what they would want, but it is there. With fixed time argument is always an invertible function. Goal of a consistency model symbolized as f theta. Right, so you have your consistency function, right? F, which is some theoretical magic function that takes you from x to x sigma, xt to x sigma, and then we're going to approximate that with our good old function approximator neural nets using a neural net, right? So f theta is the neural net that approximates the hypothetical theoretical godlike consistency function f. Any consistency function f, we have f x sigma sigma equals x sigma, i.e. f is an identity function. Let's constrain the boundary condition. Okay. So when you solve these ordinary differential equations, you have basically boundary conditions. And the reason you have these is because ordinary differential equations have there's more variables in there than there is equations, I guess. I don't know how to describe it, but you can't actually solve them. You need to start to constrain the problem in order to get a solution that even makes sense, right? So in physics, if you're using an ordinary differential equation to describe the mass of some system, you might say, okay, here's the starting mass of the system, and that is like a boundary condition, right? So here, their boundary condition is basically that it needs to match the final image, right? The final image needs to match. A valid consistency model has to respect this boundary condition. For consistency models based on deep neural networks, we discussed 2 ways to implement this boundary condition almost for free. I wonder what they mean by this. Suppose we have a free-form deep neural network. All right. Okay, so here's your... I don't like how they renamed it, but... okay, here you go. Free-form deep neural network. So you have your consistency model, which is script f theta, and then you have a different neural network here, capital F theta. And the consistency model is actually going to be a piecewise function here, right? So there's 2 parts of it. Whenever t equals sigma, which is like basically very close to 0, very close to the original image distribution, you're going to choose x. Whenever t is anywhere within, not anywhere outside of that, right? So basically, if we're here, it's just going to be the image. If it's anywhere beyond there, so anywhere from here, here, and here, then we're going to choose this model here. So it's kind of like this piecewise function. The second method is to parameterize the consistency model using skip connections. Okay, skip connections, that's the ResNets, right? So basically channels of information highways, they were called sometimes, but paths through the neural network that can skip through modules. ResNet. Right, this is a perfect image right here. So you have here, this is a convolutional neural network, and you can see how the input has to go through all this crap to get to the final output, right? But you can have these skip connections, right, that just say, okay, well, I'm also going to take the input here, and then rather than having it go through all this crap, I'm going to make it go around, and it can skip all these layers, right? So that's what a skip connection is. And that's what ResNets are based on. But they're pretty much everywhere now. There's ResNets and transformer, or there's skip connections and transformer models, and I would say almost all modern architectures have skip connections, right? So our function here, f theta x of t, which is itself a little piecewise function, is the combination of x, right? And then f theta xt, also a neural net. But these are parameterized by the same theta. So these aren't 2 different neural networks. It's just that this is kind of like a function which is composed of a neural network and then just this other flat part here. C-skip and C-out are differentiable functions such that C-skip at e equals 1 and C-out at e equals... Okay. So at time step sigma, which is basically the beginning, this will be 0, right? Which means that this term will disappear. And then the value of f theta will just be x, right? Because this term is 1 and this term is 0. When you flip it, at time step capital T, it's not going to be that case, right? It's going to be, this is going to be 0, and this is going to be 1. This way, the consistency model is differentiable at t equals epsilon if f theta xt and scaling coefficients are different. Everything has to be differentiable, which is important. Which is critical for training continuous time consistency. Continuous time here basically means that the trajectory needs to be continuous. Parameterization bears strong resemblance. Coffee, there's water. To many successful diffusion models. Topology. I wonder if this is... There's no way that that's the... Could be. No, he's pretty badass at math, so... He's writing diffusion model papers without people knowing. With a well-trained consistency model, we can generate samples by sampling from the initial distribution, just noise distribution, Gaussian, and then evaluating the consistency model that involves only one forward pass. Right? So once you have this consistency model that kind of generally works from any intermediate time step to the original image, then you can just start from a Gaussian and say, okay, well, I'm at time step capital T, take me to the original data distribution. And I'm curious to see how good it does, though, right? I imagine that if you start from a lower time step, it'll perform much better than if you start at a higher time step. All right, so here we have an algorithm, multi-view, multi-step consistency sampling. So inputs to this algorithm, like what do you need to do this algorithm? You need the consistency model, right? So this is your trained neural net. You need a sequence of time points, so you need a bunch of times, tau 1 all the way to tau n minus 1, and whatever your initial noise function, right? Or your initial noise, which is a probability distribution of Gaussian with centered on 0 with a squared variance. Okay. X from f theta, so have f theta is your consistency model. It can map from any image and any point in time backwards to an earlier point in time. So that's basically what they're doing here. Saying, okay, I have my noise and I have at time step capital T, map that back to the original image X. And it says, okay, mapped back. Now for n, going from 1 to n minus 1, so going forward in time, sample noise. So here's a noise that you're sampling. Then say, okay, X, right, the image plus that noise, right? And here's like some kind of special tau squared n is basically just the time step minus this tiny epsilon squared. So this is just like basically modifies the noise based on the time step, makes it bigger or smaller, and you add that to your image here, and you get the image now with the noise added, right? Which means it's further along in time. It has become closer to the pure noise distribution. And then you do the same thing again. You say, okay, well, now I'm going to take this image, which should have a little bit more noise, and I'm going to say, map it back to X. All they're doing here is getting the image, adding noise, feeding it back into the thing, getting the same image, adding noise. One can also evaluate the consistency model multiple times by alternating denoising and noise injection steps for improved sample quality. Huh, that's kind of cool. This multi-step sampling procedure involves the flexibility to trade compute quality. It also has important applications in data editing. In practice, we find time points in algorithm where the time points are pointed at one at a time using terms to optimize the FID of. Okay, so this is interesting. A sequence of time points here doesn't necessarily mean just like 4, 3, 2, 1, right? It doesn't necessarily mean like the 4 points that just lead back to the original one. It can be any point, right? Any amount of points, right? You can go from step 10 to step 2, and then to step 8, and then back to step 5, and then back to step 0, right? So basically you have some weird set of points, and you're either, if you're going backwards, you're going to add noise, or if you're going backwards, you're going to remove noise, and then you're going to add noise. So it's actually kind of cool because it's not, the multi-step sampling is not going just backwards, back. It's not just remove noise, remove noise, remove noise, remove noise. It can be remove noise, add noise, remove noise, add noise, remove noise. That's pretty cool. And then they're going to choose which of the points are the best, right? So they're going to basically use this ternary search, which is a kind of like a numerical method of solving. The greedy algorithm just basically means that there's a lot of possible different ways, like choose the time steps that eventually lead you to the image. So they're just going to greedily pick the one that optimizes the Frechet inception distance. Consistency models enable various data editing and manipulation applications for a shot. They do not require explicit training to perform these tasks. For example, consistency models define a one-to-one mapping from Gaussian noise vector to a sample. Yeah. Similar to latent variable models like GANs, VAEs. So latent variables here, right, just refers to the fact that in a GAN or a VAE, generally you're working in kind of this embedding space, right, the latent space. And this is also the case for diffusion models. I think a lot of diffusion models don't actually operate in the image space. They operate in this latent or embedding space. Usually because the latent and embedding space is much smaller dimensional, so it's easier to kind of deal with, right? You end up getting faster. Consistency models can easily interpolate between samples by traversing the latent space. Okay, so I guess you can also do these consistency models using the latent space. As consistency models are trained to recover X sigma from any noisy input XT, where T is between sigma and T, they can perform denoising for various noise levels. Moreover, the multi-step generation procedure is useful for solving certain inverse problems in zero-shot by using an iterative replacement procedure similar to that of diffusion models. Replacement procedure by that. I guess if you're doing colorization and image editing, you can basically kind of mask out or like have an existing value for the image. I don't really know what they mean here by iterative replacement. We present our first method for training consistency models based on distilling a pre-trained score model. Trained score model. That's the pre-trained. Our discussion revolves around the empirical probability function ordinary differential equation obtained by plugging in the score model into the PFODE. Consider discretizing the time horizon in n-1 subinterval. Okay, so basically taking your epsilon and your t and cutting it into little chunks, right? And these little chunks are a sequence of time points, right? With boundaries t1 epsilon less than 2 less than t. So each of these points is going to be leading. Each one is going to be bigger than the other one, and they're going to lead final time step t, which is the pure noise. We follow Karras to determine the boundaries with the formula. So this is one boundary condition. So this looks like a very complicated function here, but it's, you actually look at what the different parts of it are. None of these parts are actual like variables. It's just a very complicated function of epsilon, which is that 0.002, n-1, which is just the number of points, and then rho here, which is just some hard-coded number 7. So this looks complicated, but this is just some number. It's just like a magical number here that changes with respect to how far along you are in that time. Why this rho equals 7? No idea. That's dark art stuff right there. When n is sufficiently large, we can obtain an accurate estimate of xtn from xtn plus 1 by running one discretization step of a numerical ODE solver. Okay, so xtn, this is the image at time step t sub n, and this is the image at time step t sub n plus 1. So these are basically like two images that are right next to each other, right, in terms of like how far along the time. Then they do one step of this numerical ODE solver, and it's going to give us this estimate. X hat Tn sigma, or phi, sorry. And this x hat tn phi is equal to x tn plus 1, so this one here, image at the further point in time, plus the distance between them in time, so this is the difference between those two steps in time. And remember that this is the way that these are set up. It's always going to be this is always going to be negative, actually, right? Because this is always going to be a bigger number than this. And then you have this function here, capital Phi x tn plus 1 tn plus 1, and represents the update function of one-step ODE solver. So this is basically just the ODE solver, which we saw. There's a Hune solver, and there's a Euler solver, and there's probably a million solvers. Actually, we can actually come. What are some other ODE solvers? Which are the most popular? Oh no. What a scrub move, guys. Wow. Absolute wreck, dude. Wasted. What are some other ODEs? For example, when using the Euler solver, we have phi xt sigma equals, or phi xt phi equals negative t s phi x, which corresponds to the following update rule. Okay, so if you're using the Euler solver, you can basically, instead of having this term here, you just plug in this, which is Euler solver, and then now you have this, right? And this little s phi is the what they call the score model, right? For simplicity, we only consider one-step ODE solvers in this work. Okay, so there's other solvers that have multi-step. Here you go. So multi-step methods include Adam-Bashford, Adams-Moulton, and backwards differentiation formulas. What are one-step methods? I guess one-step methods are Euler, so maybe this. Seems like implicit Euler method. Runja-Kutta. Vaguely remember this word. Or I guess two people's. Line Simpson predictor, Adams Bashford Moulton predictor. Like, at what point is there too many names to add? Due to the connection between PFODE and the SDE, one can sample along the distribution of ODE trajectories by first sampling X from P data, then adding Gaussian noise X. Specifically, a given data point X, we can generate a pair of adjacent points. Given a data point X, we can generate a pair of adjacent data. So basically, give me an image distribution X, right? The distribution is P data, the image is X. Add noise to it, and now you have X Tn plus 1, right? So you can arbitrarily generate these pairs of points by basically adding noise to any previous point. Efficiently sampling, followed by sampling from the transition density of the SDE. Computing x hat t sub n phi using one discretization step of the numerical ODE solver. Afterwards, we train the consistency models by minimizing its output difference on the pairs. Okay, so this is the actual loss. And you want the loss. Okay, I see what's going on. So these 2 points here, right? X hat t sub n of phi and x t sub n plus 1, those 2 points should be basically the same, is what this loss function is saying. right? So you have here one, and then here's the other one. God. Right? So you're using your same model here, f theta, same model which we saw up here. This consistency model, which is kind of a piecewise of two different parts here. And ultimately, there's a neural net in there. And when you give the neural net x tn plus 1, tn plus 1, it should give you the same thing as when you give it x hat tn of phi and tn. And so x hat tn of phi is after you do one step using the ODE solver. And they're calling this the loss for consistency distillation. It's a function of theta, which is the model parameters, and then theta superscript negative, or whatever you want to call this here, where superscript negative is a running average of the past values of theta during the course of the optimization. So kind of like a... See this? I've seen this in reinforcement learning before, where like people will use the average of a model, right? Like if you have a model that changes over time, sometimes what you want to do is rather than use the most latest version of the model, you basically take the last couple versions of the model, the weights for those, right? In this case, I mean model as in like a neural network, right? Like the weights of a neural network, and you take kind of the average of those weights. That's what they're doing there. The expected value, that's what this fancy script E means, and it's the expected value of this term here. And they're saying the expectation is taken with respect to x, sampled from p data, n sampled from a uniform distribution. So that's what this like fancy script U here means. It basically means a uniform distribution from 1 to n minus 1. And x tn plus 1 in the, or from the normal distribution of x and t squared. So this is the normal, the Gaussian, aka the noise. Lambda, this random little magical term here, is a positive weighting function. So it's this script R just means real number, right? So it's some number from basically 0 to infinity. And D is a metric function. So a metric is just a way to measure a distance between two things, right? That's the most general definition. So a metric can be the distance in a Cartesian coordinate system, right? That's a type of metric. So here, there's some metric that you can use to say how far away is this term here from this term here, right? And I bet you they're going to use the FID or something. No, here you go. They're going to use the learned perceptual image patch similarity, LPIPS. Okay. And that's the one that they use. Or actually, no, never mind. They used that one. They considered that one, but they also considered just like a much simpler one, like an L1 distance, and then also an L2 distance. So why do they have like learn perceptual image patch similarity instead of just like an L2 distance? It's because if you had a picture of a doggo that was wearing a red sweater and a cat that was wearing a red sweater and then a cat that was wearing a blue sweater, if you just use L2 distance, the distance between the dog wearing the red sweater and the cat wearing the red sweater is actually closer than the cat wearing the red sweater and the cat wearing the blue sweater, because the distance in pixel space, it's more about like how many of the pixels are the same, right? So if there's a lot of red pixels, the distance is going to be smaller. So you want something that represents more the distance in kind of semantic space, right? You want to say, okay, the cats should be closer together because they're both cats versus the cat and the dog. So this is why you need kind of a special metric that tries to have some semantic knowledge in there. And usually the way that people do this is they'll take images and they'll basically encode them with some pre-trained image encoder like a VGG or some kind of ImageNet, ResNet or something, maybe like a VIT, Vision Transformer, and then that will give you an embedding, right, a vector, and then you take the similarity or the distance of those two vectors, right, and the vectors for the cat in the red sweater and the cat in the blue sweater are going to be closer together than the vector for the dog in the red sweater. So that's why choosing the right metric, especially in images, is important. For distance, blah, blah, blah. Okay, so in this equation, they have the expected value, the loss is the expected value of this crap, and then they have this magical lambda term here, like lambda t sub n, and you're like, oh, okay, wait, so there's going to be this complicated like weighting that's dependent on the time step. And then you scroll down and you find out that lambda t sub n is just 1. So if that's the case, like, why not just get rid of this lambda t sub n? Like, why have this additional complication? Just remove it. Just substitute 1 in there and cancel it out, and then it reads easier, and then it's easier to understand and read this paper, right? It's really annoying when they're like, when you see these multi-part loss functions, and instead of, and like the weights for the loss functions just end up being 1, right? At that point, you don't have the weights in front of the loss function. In practice, we minimize the objective by stochastic gradient descent, old SGD, on the model parameters while updating with exponential moving average. So this is the most recent version of the model, and then this is basically like kind of like a lagging version of the model that updates more slowly over time. It's the average of the previous models. And there's also a decay rate. Okay, so they also have kind of basically a weight decay. And weight decay is, right, if you think of the weights inside your neural network, right, your neural network is really just this giant collection of weights, right, this giant set of weights. And the exponential moving average of those is just the average of all those weights. But then you can also do weight decay, which basically means that every time step, the weights kind of just like erode it, right? And what that means is that if you just if you happen to take gradient steps and some of those weights become useful, right? Like sometimes it's you don't want that one weight that was useful for that one time step to basically dominate for the rest of time. So by having weight decay and you're constantly just eroding these weights, only the weights that are consistently useful and like over time and like keep giving you correct answers, only those survive, right? And the ones that like are only useful for one thing or maybe one step, like they over time kind of erode and become 0, right? So that's how weight decay can help improve the weights in your neural network, kind of act as a regularization where it basically, it's almost like a survival. It's like evolution for weights, right? It's like they're constantly going to be decreasing, so they better be useful and they better increase over time because of the stochastic gradient descent, or else they're going to erode. The overall training procedure is summarized in algorithm alignment with the convention and momentum-based contrastive learning. So deep reinforcement learning is just reinforcement learning, but with deep neural networks, where the deep neural network is usually used for the value function or the policy. We refer to F theta negative as the target network and F theta as the online network. So in reinforcement learning, right, you have the collection of experience and then you have the training of the network. So let's say you have a bunch of AIs that are playing Go, right? You have AIs running on a computer that are playing Go, and they're collecting experience, right? They're collecting interactions with the environment. And then the problem is that you have that running in parallel. So you have many different AIs interacting with the chess environment and collecting experience, right? That experience was collected by slightly different AIs, which might have slightly different weights, right? And then how do you kind of aggregate that together and then have a new network that you then distribute, and then that new network is the one that plays the chess. So this kind of concept of having like a target network and an online network, right? Or a target policy and an online policy. Very important in deep reinforcement learning. Here they're basically taking that same idea, and I guess it's not the same idea, but it's like the same kind of like high level concept of having these like different networks that are basically just the same model but with slightly different weights, and how do you like basically average them together into one model with one set of weights. Let's actually see consistency distillation. You need your dataset D. You need initial model parameter theta. You need some learning rate. You need some ODE solver, right, which they said is just going to be a one-step Euler. You need some distance metric, which they said is this LPIPS. You need this lambda, which they said is just 1, so why they don't just say 1. And mu, which I guess is just the... No, actually, it might be the exponential average. No, mu is the weight decay. Bad. Mu is the weight decay at each time step. How much of the original model weights you use versus the exponential moving average model weights. Okay, so repeat basically just means a while loop. So you have a while loop here that basically repeats this until convergence. Basically means until someone shuts it down. You sample X from the data set, so that's an image. You sample some time step, so you sample an arbitrary time step from a uniform distribution from 1 to n-1. You sample the time at tn+1, right, which is going to be noise. You say this image plus noise, right, an image that's further along in the progression of time at which it becomes pure noise at time step capital T. So this image is going to have more noise, right, because it's at a further time step. You're adding to it the difference in the time steps times the Euler, the ODE solver, right? That gives you this one here. The image at a slightly earlier time step based on the solution provided by the ODE solver, right? So here you have the image tn+1 at a later time step. Here you have the image tn, which is earlier time step, should have less noise, and it's based on the ODE solution. You have your loss, so now you have to calculate the loss, and the loss is the distance metric, right? This d, this metric, and the distance is between your f theta, which is your consistency model, right, which is a neural net, and the consistency model or neural net that is parameterized by the exponential moving average of the weights, right, with some weight decay thrown in there as well, right? So you optimize that this loss function is going to be used here to update theta, right? So at the end of the day, this loss is what allows this term here, gives you, right, you take, this is just gradient descent here, so you have your loss that you just calculated. You say, okay, what is the derivative of this loss with respect to my weights theta, right? This is the chain rule here. You use the chain rule along with the learning rate, right, which basically just says how much am I moving, right? A small learning rate means that your weights are moving very small steps. They're changing very small. A larger learning rate means that your weights can make bigger changes, bigger steps, right? So all this is doing here is just saying, okay, the weights of my model minus whatever my learning rate is times the derivative of the loss with respect to the weights of my model, and that gives me the new weights of my model, theta. And then I'm going to find out what this theta negative, theta minus here, theta superscript minus, like what would you guys call this? theta with like a negative in the superscript, but it's basically the exponential moving average, which is just, okay, I have this new theta that I just calculated with one gradient step. I'm going to multiply it by this weight decay so that over time it kind of like decreases. And then I'm going to set that to my theta negative, and then I'll basically just repeat this, right? And I guess convergence here will probably be defined by the distance metric. So at some point, this distance metric d is probably going to be small enough, and then you're going to say, okay, I guess it's now small enough that we can exit this while loop. I don't know, or maybe the convergence refers to the whenever this theta superscript negative becomes theta. So if theta superscript negative and theta become close enough, maybe that's when the convergence stops. Okay. Below, we provide a theoretical justification for consistency distillation based on asymptotic analysis. This is probably the hairiest part of this entire paper right here. Oh no, it's going to be even more. Look at this. You got a second theorem. Like, when people are breaking out theorems, these math papers, this is where you have to pray to the gods. Okay, so theorem 1, let delta t be the max n, or the max of n from 1 to n minus 1 of tn minus n plus 1 minus tn. So delta t is the maximum distance in time space between any pair of samples, right? So I think delta t should basically be capital T minus sigma, if I had to guess, right? Because that's mapping all the way from the end to all the way from the beginning. You have your consistency function. Assume f theta satisfies the Lipschitz condition. Guy's name is literally Lipschitz. Sucks. Where there exists L greater than equal to 0 such that for all t, right, all possible types of t, x's, and then y, where I guess y is the target. Or no, y is this here. So you have your consistency function or consistency model. It's taking xt and it's taking y and t, and it's the difference between those, right? The L2 distance, right? The L2 distance between those should be less than the L2 distance between x and y themselves. That's weird. That doesn't really, because this consistency function should change the dimensionality of this input such that x and the difference between x and y and the difference between x and y after they've gone through the consistency function, I think that's, how do you compare them with this? Assume further that for all steps, the ODE solver has a local error uniformly bounded. Have some error bound here. Then, if the loss is equal to 0, have okay, so basically they're saying for any pair of steps that we sample, feed them through our consistency function, the difference between those is going to be less than whatever the error that the ODE solver is bounded by, right? So each ODE solver has some theoretical guarantee around the error that it can produce, right? And that theoretical guarantee about what the error bounds are that is specific to the ODE solver, and then each ODE solver is probably going to have all kinds of like crap that you can use to calculate the theoretical error bounds. And then it's basically saying the difference between these is going to be equal to the error bounds in some magical way, right? Like hand waving induction proof, classic proof of global error bounds for numerical ODE solvers. Right? Like this is, I think it's a little bit unnecessary here. I think they could have probably just said the error of this is matches or like is bounded by the whatever the global error bound is for our numerical ODE solver. So you can actually say here, which ODE solvers have the smallest error bounds? I somehow bet you it's going to be. Start a new chat. Depend on the type of solver and the specific method employed. Generally, the error bounds can be categorized into local truncation error, LTE, and global truncation error, LTE. Okay, cool. Both these errors depend on the step size, the order of the method, right? So if you remember, Euler is a first order method, and the hewn is a second order method. There isn't a one size fits all. Okay, so basically, individual ODE solvers aren't going to necessarily have specific, like consistent error bounds. It's going to depend on a bunch of things. So ChatGPT basically gave us the answer of it depends. RW, I have to up my math skills. I'm totally with you, RW. This is right kind of at the limit of what I'm capable to understand, if I'm even understanding it. So, but I think this is honestly probably the most intense math that we've had on this channel up until now. This is a very like dense paper. Okay, since theta super negative, that's I guess what I'm going to call this, super negative, is a running average of the history of theta. We have theta negative equals theta when the optimization algorithm. Okay, so up here we were looking at this algorithm. We said, okay, it's repeating this process until convergence. What does that mean? Convergence here means that the exponential moving average of the weights and the weights that you just freshly calculated with your gradient descent step are the same. This is probably not equals. There's probably some threshold here, right? I think this equal sign here is supposed to be the little squiggly signs, approximately. That is the target online consistency target and the online consistency models will eventually match each other. I feel like it's like impossible that they actually match each other, right? It's like they're going to be close, but like if they're float 32s, they're never going to actually equal each other. If the consistency model additionally achieves zero consistency distillation loss, then theorem 1 implies under some regularity condition, the estimated model can become arbitrarily accurate. As long as the step size of the, okay, yeah, that's why. And I think there's like, you have to take these kind of like error bounds and like with a grain of salt, right? Where it's like, as you go to infinity, it'll become X, right? But it's like, you're never actually going to go to infinity. So proving that it has a certain behavior in the limit isn't necessarily useful in the real world, right? So like, oh, I came up with this loss or this particular solver that as you go to infinity, it becomes exactly what we want. It gives you the exact distribution, right? At the limit is a way to describe that. But the behavior at the limit isn't indicative of the behavior in the real world, because in the real world, you're never operating at infinity. Nonetheless, they involve Jacobian vector products and require forward mode automatic differentiation. May or may not be well supported in some deep. So some deep learning frameworks do not work well for this. I bet you, like, I mean, did they use anything that isn't PyTorch? We have algorithm 3, consistency training. So these are the two different types of training. They have the consistency distillation and then they have the consistency training. They start with the same things. They have some data set D. They have some kind of initial model parameters theta for your consistency model. You have a learning rate. You have your step schedule. And you have your exponential moving average with weight decay that has some weight decay term here, has some distance metric, and then it has the kind of like this is also a repeat until convergence, so just some while loop here that goes until it ends. Looks very similar, right? Sample X from the distribution, and then the step from the uniform distribution. Same step here. Here, you're sampling noise, right? You're sampling some noise vector from normal. Here, you're sampling the actual image. You have the loss, right? You can see here that the loss no longer has a dependence on the ODE solver. So here, the loss was dependent on the ODE solver. Here, it is not dependent on the solver. You still have your distance metric between those, and you see here the two things that should be the same in this particular thing here are your consistency model when you give it the image X plus the time step times the noise, and then here the image X plus the time step the one before that, so the previous time step plus the noise. So basically the I'm going to use their words here. So the target consistency model's output of the image with noise at time step t sub n should be as close as possible to the online consistency model's output given the image plus the noise at time step t sub n plus 1. All of that weighted by lambda, which we've been. And you have your standard gradient descent here, right? You have your loss function. You have the derivative with respect to your loss function of. You have your learning rate, and you take your current weights. You subtract whatever step your gradient descent tells you, and you get your new weights. And here you have the exponential moving average, weight decay. And you go from k. See how here they go nk minus 1, add k, add 1. It's like k plus equals 1. Training consistency models in isolation. Consistency models can be trained without relying on any model. This differs from diffusion distillation, making consistency models independently models. Yeah, so basically we've seen how they can train these by using a pre-trained diffusion model, because in a pre-trained diffusion model, you have every intermediate step that the diffusion model takes from noise into the actual image. So, okay, I have a stable diffusion model, and it takes me from this noise to this image, and here are all the intermediate steps. Well, I can take every single one of those intermediate steps and create these pairs of like time step t minus x, and then time step t minus these two, and these two, and this one, and this. Basically distill your consistency model from the pre-trained diffusion model. But they say, hey, you can actually take this consistency model and then train it from scratch. And because you can train it from scratch, it's no longer using diffusion models in any way, shape, or form. So it's a new type of model, right? And that's kind of what they mean here by it's a new independent family of generative models. Independent here, I don't know if that necessarily has like a specific mathematical definition. I just guess it means they're saying, what it means is that they're saying this is a slightly different thing. it's not just a diffusion model with some bells and whistles attached. In consistency distillation, we use a pre-trained score model to approximate the ground truth score function. To get rid of this dependency, we need to seek other ways to estimate the score function. In fact, there exists an unbiased estimator of the score function due to the following identity. Okay, so they have this score function, and then they said, okay, we're going to approximate this score function with a model, right? And we're going to call it the score model. And this score model is basically just the expected value of the image at time step t minus the image over the time step squared conditioned on the time step t. Right, so given this parallel bar here means given. So given x of t, you basically just subtract x, divide by t squared, and that's your score function. So, you know, they were setting up this boogeyman the entire time in this paper, this score model, this score function, right? And we're like, oh no, it's going to be extremely complicated. It's going to be all kinds of crazy shit. And then you come and it's literally just xt minus x over t squared. So this score model, which I kind of thought it was going to be this scary, complicated thing that I'd never heard of, and here it is, and it's literally just the difference between the image at time step t and the image at time step t. So, whew. X is sampled from the distribution of images, and xt is normal function. Given x and x of t, we can form a Monte Carlo estimate. Monte Carlo is basically just kind of a brute force. You want to think of it that way, is kind of similar. It's like actually doing the thing, right? It's like actually running and getting a bunch of points and then getting an estimate of the actual function from the points. We now show that this estimate actually suffices to replace the pre-trained model in consistency distillation when using the Euler method or any higher order method as the ODE. More precisely, we have the following theorem. Okay. Almost at the end here. We got one more theorem that we got to get through. So let's go ahead for Narnia. We're doing this for Narnia. We're charging at this. All right. Starts off very similar to the previous one. You have some delta t, which represents the difference in time between some time step tn plus 1 and some time step t, right? For any 2 points, 1 to n minus 1. Assume d and f theta are both twice continuously differentiable with bounded second derivatives. So the consistency model that is the target, right? The target consistency model, which is basically the exponential moving average of the consistency models. They say, okay, assume it is differentiable. And because it's a neural net that you're optimizing with gradient descent, it's going to be differentiable because it needs to be differentiable to even do that. The weighting function lambda is bounded. And the expected value of this term here, which is the score function, is less than infinity. So the score function is always going to give you a number that isn't just infinity. Assume further that we use the Euler ODE solver. Okay, so they're using the simplest first order solver. And the pre-trained score model that matches the ground truth. I feel like this is a very strong assumption. And the whole point of this is that they want to go from this loss function, which includes the Euler ODE solver, right, this phi here, and they want to go to this loss function that does not include that, right? So here you see this loss function is equal to this loss function, which is only a function of theta and theta super negative here, plus this extra term here. O of delta t. What is this O of delta t? Consistency depends is defined as. Fuck did they define this O delta t? They do not. They don't even tell us what the fuck. Some function which uses the difference in time. Okay, so the consistency training objective, this is the loss. So this loss here is equal to this, which is actually one of the earlier equations we saw. The noise is sampled from a normal distribution. This I here, so like I've explained this like a million times, and I'm sorry if you guys already know this, but you have your normal distribution. The 0 here means it's centered on 0. It's a Gaussian centered on 0. And this capital I is the identity matrix, right? And what that means is that the variance is the same in all dimensions, right? So if you have a 2D Gaussian, this is a Gaussian that has the same variance across both dimensions x and y. This is a Gaussian that is 2D but does not have the same variance across x and y, right? So when you see this script n0i, it basically means it's a Gaussian in some higher dimensional space, potentially two-dimensional, potentially infinite dimensional, that where the variance in each dimension is the same. The proof is based on the Taylor series expansion and properties of score function. We're just going to take them on their word that this is all kosher, and we refer to equation 10 as the consistency training loss. The L theta theta negative only depends on the online network and the target network. So really the reason they're doing this is because they want this loss to only depend on the networks and not on this additional ODE solver. Oh shit, no. Phi is not the ODE solver. Phi is the diffusion models. Okay. Phi is like the stable diffusion. That makes more sense. So they don't want a loss that is dependent on the external pre-trained diffusion. Decreases at a slower rate than the remainder. Okay, so O of t is the remainder, thus will dominate the. And goes to infinity and delta. For the improved practical performance, we propose to progressively increase n during training according to a schedule function. Okay, so we've seen this before where the same way that you have learning rate scheduling, you can have a schedule over a variety of different parts of any kind of model training system, model training pipeline. So here the n, which is basically the step at which they're taking these pairs, is going to have some kind of schedule. Consistency training loss has less variance but more bias with respect to the underlying consistency distillations. When n is small, delta t is large. On the contrary, it has more variance but less bias when, i.e. delta t is small. Okay, so when n is small, delta t is large. So delta t is the difference between these two time steps. So whenever delta t is large, that means choosing two pairs that are very big, that are kind of far apart from each other. And saying the consistent large, or the consistent loss has less variance bias. Delta t. What does that mean? Delta t points are further less variance, that the trajectory delta t is variance is going to be bigger. I don't like fully grok that, but my brain is starting to melt. According to the schedule function, the algorithm consistency training is providing algorithm 3, and the schedule functions use C. Similar to consistency distillation, the consistency training loss can be extended to time. Okay, so you don't need to be doing this in steps. You can. This continuous time loss function does not require schedule function for n or mu. Mu is the weight decay, n is time in between steps, or the number of total steps. It requires forward mode automatic differentiation for efficient implementation. Unlike the discrete time CT loss, there is no undesirable bias associated with the time objective. We effectively take delta equals 0 in theory. Okay, so once you have infinite time resolution, right, this delta time becomes infinitely small, so this remainder here becomes 0. So that's what there's this term here, 0, when you have kind of infinite time. Boy, consistent. Okay, let's just acknowledge that we finished that and we've gotten to the easy part of the paper. We now reached the experiment section. So the math is over. Now all we have to do is read about how they got CFAR 10. Is on CFAR 10. CFAR 10 is basically little thumbnail kind of images. ImageNet or LSUN bedroom. These are all very tiny image data sets. LSUN cat. I think 256, maybe these are slightly bigger data sets, but CFAR 10. They compare Frichet inception distance and inception score. I don't like these metrics very much, but they're quantitative. I generally prefer when people do kind of human evaluations. They have these images and say which one's better. I think those are the best types of evaluation metrics for generative models. We perform a series of experiments on CFAR 10 to understand the effect of various hyperparameters on the performance of models trained by consistency distillation. Various hyperparameters. We first focus on the effect of the metric function, right? So this is the distance between two images, right? And you can choose different distances, right? So we were talking about how they can choose the L2 distances, or L2 distance, the L1 distance, and the L pips. And then when it comes to the ODE solvers, they compare the Euler, which is the easy, fast one, to Hune, which is the slightly better, slower one. They also compare the number of steps, so anywhere from 9 steps, which is what the fastest diffusion models are doing, and then 120 steps, which is more, that'd be very heavy. Right? How many steps does stable diffusion? How many steps number of steps? Like when people are doing stable diffusion, they have around 25 steps. So basically straddling. They try with about half of the number of steps and then basically twice or times the number of steps. Consistency distillation and then consistency training, right? The two different ways to train this. One where you have your pre-trained diffusion model and one where you do not have your pre-trained model. The optimal metric is LPIPs. kind of makes sense. Outperforms both L1 and L2. Investigate which ODE solver is the best. Qn ODE solver. Obviously, it's going to be better. It's just slower. And then n equals 8, which is kind of surprising. I would have thought that n equals 120 would have given you the best choice. Okay, so here you have the actual charts here. You have on the y-axis FID, which is the perception distance. The higher that is, the more dissimilar images are. So as your images become more and more similar, you see it go down over time. Training iterations, this just basically means how long it's been training for. And you can see how the L2 loss and the L1 loss are both worse than the LPIPs, which kind of makes sense. And not only are they worse, but they also fall down slower. You have different ODE solvers here. So you have Euler, Hume, and then you also have the number of steps. So it's interesting that there's this big spike, right? Like you see spikes here in FID. So I wonder what that means. It means your model's like getting better, getting better, getting better, then it gets worse really quick, and then it goes, okay, getting better, getting better. Unusual. Here you have all using the same Qn solver, using the LPIPs metric, and then different number of steps. See how as you increase the number of steps, the LPIPs goes down. Interestingly, though, there's kind of a limit. You know, it's like it's not like if you keep increasing the number of steps, it just keeps going lower. There seems to be this kind of limit here that they're approaching. And then here you have consistency training, which I think is the one that's done from scratch. So these are all consistency distillation, which means that they're learning to copy a diffusion model, right? They're learning to distill a diffusion model. And then here you have training from scratch. Interesting that training from scratch, kind of you see here, the lowest FID that you get is around 10, versus when you're doing distillation, you can get FIDs of 4. So it does seem you get better with consistency distillation, consistency training. Multi-step image generation with consistency distillation. Consistency distillation outperforms progressive distillation across all datasets and sampling sizes. Okay, so progressive distillation is a different paper. They're kind of using it as a benchmark. Right here, progressive distillation from Salazman and Ho in 20. And here are 4 different datasets: CFAR10, ImageNet, Bedroom, and CAT. See how the L2 and the LPIPs are lower for consistency distillation compared to progressive distillation. Maybe not. Like right here, you actually see it's actually worse. Right, the green bars are lower than the blue bars, which is what we want, or at least what the authors of this paper want. Right here, the green bar is actually taller than the blue bar. Optimal consistency models trained by higher order ODE solvers have smaller estimations at the same end, right? The higher order ODE solver, the Hume solver, it's going to take longer, and the only reason you would do something that's longer is because it's better, and better because the error bounds on it are small. Strong connection between we adopt LPIPs for our CT experiments throughout this paper. Unlike CD, there is no need for using second order solver, and CD loss function does not rely on any solver. Yeah, right. If you remember, they went through all this trouble here. Take this loss, which was a function of ODE, pre-trained diffusion model that has an ODE solver, and then got rid of that term. Matches our analysis and motivates our practical choice of progressively growing n and mu for CT. We tune the schedules separately for images of different. We have schedules for the kind of weight decay exponential average. You have a schedule for steps. So that's not great because it basically means that there's hyperparameters here, especially the fact that they said images of different resolutions. So depending on your image resolution, you're going to want different values of those, and that additional kind of hyperparameters that are optimal for different image sizes, different image modalities. That's not necessarily great because you have to find what those parameters are and tune them like for your specific application. Are the only distillation approaches that do not construct synthetic data before distillation. I mean, in stark contrast, other distillation techniques such as knowledge distillation and DFNO have to prepare large synthetic data sets by generating samples with expensive numerical solvers. Okay, so you basically need to generate these immediate steps. Every time you generate one of those, right, is a synthetic data set of these intermediate steps you need to solve using an solver. Note that across all sampling iterations, using LPIP metric improves compared to the squared. Yeah, they keep repeating this, but it makes sense that LPIP is better than LT loss. Table 1, sample quality on CFAR 10. Here you have different samplers. IM, which I think is the most popular one. I'm not sure. People who use Stable Diffusion a lot, if any of you use Stable Diffusion a lot, you probably have a much better understanding of kind of like what these different solvers result in. I'm more of a Midjourney guy, so I don't really know what solver or what sampler I'm using underneath. Different types of distillation here. These are benchmarks. Kind of getting the best. This is inception score. Inception score is basically you take both images, you put them through inception net, which is kind of like a conv net, and then it gives you a vector, and then you compare those two vectors. It's similar to it's trying to basically give you a difference between a metric between two images that has some knowledge of kind of the semantic meaning within the image. So images of cats be closer together and so on. The StyleGAN XL. Fucking Rex. I don't know, maybe GANs are better. Maybe distillation or consistency models just get killed by GANs. Look at this. This score is like super hard column. These are all different types of generation. This is CFAR, and then this is the same for ImageNet, LSUN. I don't know. These numbers are like really hard to read. I don't really like FID or inception score. I'd rather just look at. Let's actually look. So the top is EDM. The bottom or the middle is CT plus single step image generation. Right. So this is the consistency training of this model or of this paper, but they do it in one step. And then remember that the way that this paper works, you can do it in any number of steps, right? You can do it in more steps and get better results. That's what they do here. CT plus in 2 steps. So the bottom should be better than the middle, which you do kind of see, right? You look at this cat, its face is all mangled, but then you go here and the face actually looks pretty good. And then EDM, which is, I guess, what they're comparing to, just benchmark. Honestly, the EDM looks better. Like, look at this cat's face. This cat's face. Cat's face. The background here. Way cleaner. Direct generation. Tables 1 and 2, we compare the sample quality of consistency training with other generative models. We observe CT outperforms all single-step, non-adversarial generative models. I mean, but if you compare it to generative models that are adversarial, such as GANs, and you do worse, then is it better or not? Comparable quality without relying on distance. Provide EDM samples, single-step CT, step CT. All samples obtained from the same initial are significant structural. So if you start from the same noise, you end up at the same place. I guess important. Zero-shot image editing. So zero-shot is when you take a neural network and you apply it on a new task without any additional fine-tuning. Similar to diffusion models, consistency models allow zero-shot image editing by modifying the multi-step sampling process. We demonstrate this capability with a consistency model trained on Olson bedroom dataset using consistency distillation. Shows such a consistency model can colorize grayscale bedroom images at test. Generate images based on stroke inputs. Okay, so basically these are not image generation tasks. They're colorization, super resolution, and stroke guided image generation. All that means is that the user kind of draws. See here in the very beginning, they draw like this is wall, and this is bed, and this is pillow, and then that is used to condition the generation. And then on the right here is the ground truth. So this is what it's actually supposed to look like. The very last image here, and then the outputs of the consistency model. Pretty good. I like all these like hallucinations that it does for the head. Conclusion. We have introduced consistency models, a type of generative model that are specifically designed to support one-step and few-step generation. Empirically demonstrated that our consistency distillation model outshines the existing distillation techniques for diffusion models on multiple benchmarks and various sample generations. Furthermore, as a standalone generative model, consistency models outdo other available models that permit single-step generation. What does outdo? Barring GANs. Our performance is the best, as long as you do not consider these other things. Sound great. They also allow zero-shot image editing applications such as in-painting, colorization, blah, blah, blah. So do all of the other generative models. Consistency models share striking similarities with techniques employed in other fields, including learning. This is the reinforcement learning that I was talking about. The Q function is approximated with a neural network. It used to not be, right? It used to Q learning existed before deep neural networks existed, and only afterwards did reinforcement learning, where you were trying to learn this Q function, which I think is the value function. Right? It's basically the estimate of the value at a certain state. And the key idea there is this idea of the target model and then the online model. And momentum-based contrastive learning. This offers exciting prospects for cross-pollination of ideas and methods along these. Yeah, so I think this is maybe the interesting part, is that maybe there's other ideas from reinforcement learning that you could apply, but it starts to get pretty complicated quick. Even this paper is just kind of. We'd like to thank all the members of the OpenAI algorithms team for a helpful project. We're all helping each other out. So what do you have in your appendices? You have some proofs. More proofs. Consistency, distillation, and continuous time. So basically when you don't have discrete time steps. Some that. Christ. Math. The expected value of the, or remainder, I think. This must have taken like 10 years of time to write all this LaTeX. So LaTeX is the programming language that you use to write these equations, papers. LaTeX, sometimes call it. But it can be very annoying to write equations. Masked images in painting. This is what CFAR10 looks like, which is kind of what I'm saying. It's like generating CFAR10 images. They're like so grainy, so tiny. That FID score on a CFAR image, like, what does that even really at? Grumpy Cat died, right? Sad. Cool. So, damn, what are we at? We're almost at 3 hours. What a marathon, guys. We've made it. We read through this crazy paper from OpenAI. That's basically a fancy type of diffusion model. It's different from a diffusion model. It has the very powerful property that you can trade off the number of time steps and the quality. So you can generate images very quickly if you need to, and then you can also generate images with many steps and higher quality. It seems like it's simpler than diffusion models, and it seems like it performs pretty well, but they keep saying that it performs the best as long as you don't count GANs. So they says it beats all the other diffusion models, but it doesn't beat the big GANs. So it could be the case that all of this consistency model stuff just disappears and becomes irrelevant because the GANs just become so good. GANs are, but cool. I like how they use a little bit of reinforcement learning stuff in here, and yeah, brings me back to. I feel like that. Neural ordinary. Oh yeah, I remember this. Yeah, this exact book or image. I have like a photographic memory for like images, but I don't have good memory for text and words and names. Yeah, see. But thanks for watching. Hope you guys were entertained, or maybe you learned something today. And drop by the Discord, like and subscribe. Let me know what you guys want to read. Let me know if I made any mistakes, or if I didn't understand something, or if you feel like there's something that I missed. TNN depth. Yeah, so it's like the depth of the network is the time. Wasn't that the ODE network is basically like a vector field which continuously transforms the state. So rather than having these discrete kind of like layers within a neural net, you basically just describe this vector field information in and out, kind of like an infinite resolution neural net, something like that, right? Yeah, so you see here the depth is 1 to this like a specific number of layers. All right, guys, I need to head out, but it was awesome. Thank you.